İngilizce hazırlamıştım. İngilizce mi sunayım? Türkçe mi?
Nasıl dilerseniz hocam.
Öyle mi? Peki o zaman. In this study, we have compared the adsorption capacities of nanostructured calcium silicate, rice hull ash, activated carbon for lead, zinc, and copper ions in the aqueous medium. The material nanostructured calcium silicate is produced in our laboratory from rice hull ash. It's an agricultural waste, and with a very simple process, we have produced it, and we have compared its adsorption capacity with the industrial product, very common product, activated carbon's capacity. Its production is very easy. If I would like to tell about it a little bit, we take the ash, we reburn it at 600 Celsius, and we extract the silicon dioxide content of it with sodium hydroxide into the solution as sodium silicate. Then, taken with the sodium silicate solution, we treat with calcium chloride to precipitate calcium silicate. During this process, there are some little tricks. We add some water for inhibiting the co-precipitation of other salts like sodium chloride. And after the precipitation, we also treat the suspension with spacer named compound, like the ethylene glycol, to avoid the formed framework of the product. So our aim actually is to produce nanoporous structured calcium silicate. We have taken this method from a patent of a Venezuelan scientist. They have done it at the beginning of 2020s. Now, we use this process very widely to produce calcium silicate, nanostructured calcium silicate. When we compare, okay, for the adsorption capacities comparison of heavy metal ions of these materials, we have taken 0.1 gram of each adsorbent or each material, and we have treated 50 milliliters of solutions containing lead, zinc, and copper ions. In the pretreatments, to define the optimum pH, the optimum time, and the amount of the adsorbents, we have done some experiments, and we have found that around pH 5 and 6 for 2 hours treatment is enough to obtain the equilibrium conditions. Then we have treated one by one each ion with our adsorbents, again one by one separately, with the different amounts of or different concentrations of these ions solutions. Then we have obtained the equilibrium curves or the capacity curves of these metal ions for these materials. To do this, it's very simple. We already know this initial concentration, C0, like 25 ppm or 50 ppm. In CE, the equilibrium concentration of the metal ion, which is left in the solution after adsorption of ion by the adsorbent, then we have some left ions in the solution. We analyze this using the atomic adsorption spectroscopy. And W is here the amount of the adsorbent. Using this equation, this very, very common equation, we have calculated the adsorption capacity as QE. And its unit is milligram per gram of adsorbent. And using this equation, what we have obtained, this equilibrium curves we have obtained. This is copper. Let me start with lead. Okay. As you see here, this is the result of lead adsorption equilibrium study of 3 materials: activated carbon, rice hallash, and calcium silicate. In this diagram, you see this is the calcium silicate adsorption curve, the capacity. As you see here, calcium silicate is calcium silicate is absorbing lead ions higher than the activated carbon and rice hallash. Activated carbon, you see here, is around 15, but calcium silicate's capacity is around 50. So it's higher than 3 times the capacity of calcium silicate. The lead adsorption capacity of calcium silicate is higher than activated carbon's capacity, almost 3 times. And similarly, the rice hallash capacity, because it's also a silicon oxide containing compound, actually, it's a mixture. And this is the original, our original ash. We have only reburned it, and we have taken from industry, right, trace region, and rice industry, of course. Its capacity also is higher than that of activated carbon for lead adsorption. For the copper adsorption, similar results we have obtained, but the adsorption capacity here, you see, is around 30 for lead adsorption, around 20 for activated, rice hallash, and for, again, activated carbon here, red line, is around 15, the adsorption capacity. The zinc adsorption properties or capacities is little different. You see here, again, calcium silicate is high, its adsorption capacity, but around 30, not around 50. So zinc is less adsorbed by 3 of the materials it's seen. And the rice hallash capacity of zinc is almost similar to activated carbons, or its level. And the most easily adsorbed ion by the 3 of the adsorbents materials is lead, and zinc is less or weakly adsorbed material. And also there is another thing here. I'm sorry. Also for the higher 300 ppm lead, this is lead. Also for higher concentrations, our lead adsorption capacity is so high for calcium silicate. This is very important because these materials are mostly used in mining industry, mining effluents, and they're containing large amounts of lead, zinc, copper, etc., arsenic. So it means calcium silicate can be used also very safely in mining industry waste treatments, it says to us. The zinc is an interesting element here, ion, for the absorption of our materials. There is a Irving Williams affinity series in the literature. It's shown by Strelko and Malik. They say that in the Irving Williams affinity series, they follow the order, the atomic size order, mangan, cobalt, nickel, copper, but zinc doesn't obey this rule, they say. So and they say that copper is activated over than the zinc values. And they explain this. The reason of this is explained by the scientists that the copper absorption affinity of activated carbon, they have shown this for activated carbon, but the same result we have found for calcium silicate and rice silage. It's the same, it's shown the same. So they found that for activated carbon on this. Among all the cations, they have analyzed all these ions. Because of the formation of distorted and more stable octahedral complex of copper element on the surfaces, the adsorption is higher than the zinc adsorption. Zinc is weakly adsorbed or weakly attached on the surface. That's it. Okay. As the conclusion, I can say our laboratory produced new product, nanostructured, nanoporous, which in which the pore sizes, pore diameters are around 520 nanometers. We have found this by TEM analysis, transmission electron microscopy, but I didn't give here. We have given somewhere else. Because of its nanostructure, its heavy metal adsorption capacity is much more higher than that of activated carbon, which is an expensive industrial product used in industry, actually. I can say that we can use safely calcium silicate for the adsorption of, especially mining effluents, high concentration, heavy metal ion effluents. That is my